Okay, so this PN junction transient, the problem is as follows here. We have a diode and we have a resistor connected, load resistor connected here, and the voltage across the diode we switch from a forward bias to some reverse bias here, VF to VR. So when it is VF here, forward bias, there's enough voltage here to forward bias the diode and cause a current to flow here, right? And then what happens is at a certain time, we abruptly switch it to negative voltage here. And when we switch it to negative voltage, we obviously expect that the current through the diode should drop to zero here. But it doesn't immediately drop to zero. It takes a certain time for the diode to switch off here, right? So what we want to know is how much time does the diode take to switch off? Okay. And this is a model that you must have seen in the notes. That diode we are modeling as in the forward bias case, we are modeling the diode as a current source, a voltage dependent current source here, where current goes in general IS exponent QV. I should have put here N ideality factor, NKT minus 1 here. So this is my current, voltage dependent current here. The diode has a junction capacitance, Cj, and the diode has a diffusion capacitance, Q by KT. I naught is this I naught here, multiplied by some lifetime term naught, right? So this is the model here. If you remember the model of a diode which is shown here, we've also said that this we have said that the model of the diode that you see here is, there's a name you must have seen in the notes also, that this is a quasi-static model here. When we write these expressions, these are all based on quasi-static model here. What does that mean? What does it mean? Quasi-static model. Then how can I use it for understanding transients? If the transients have died down, then how can I use it for understanding transients? If it's steady state, then why am I doing transient? No, what? Not really. We are using it to understand transient. We are doing it. We are using this model. We'll do it now to carry out transient analysis. But note that during the transient analysis, what we are saying is that the behavior of the diode is more like the same expression that holds in DC also holds under transient. The only thing that differs is that V, it becomes a function of time. The expression remains the same. And this capacitance, for example, if you look at it, we calculated by assuming a certain profile of the injected hole density. How do I get that injected hole density profile? From steady state calculation. So we are assuming that the profile still remains the same, even under transient condition. This P, for example, the injected holes that are there, the holes may be changing with time, but the shape still remains the same. The shape still remains the same. Okay. So, all right. So we'll discuss this in a little bit more detail. What the implications of this quasi-static model are. Anyway, so this is the model that we have. Okay. And based on this model, we would like to understand how does my diode switch. Okay. So what I'm going to do is, in this, take this particular diode out, right, and substitute this particular model. Okay. So let's do that. I've taken the diode out and substituted the model. And I'm specifically now looking at which situation? I'm looking at a situation that it was already forward biased, some current was flowing. Now I have put it under reverse bias. So I'm looking at, let's say we call it time t equal to 0. And I'm looking at from time t equal to 0, then further on. Okay? And so the diode has been reverse biased, so that's why we put reverse bias here. The diode has been substituted by this model here. And now what is happening? Diffusion capacitance is given here, the current is given here, and this is the junction capacitance. Now, what I'm going to further assume is that so a certain current would flow. Why will the current flow? What is the source of the current? The capacitance is discharging. Are you seeing now what is happening? I've put an arrow here. This capacitor discharges. as it discharges, it gives a current here. Where does it current go? Current flows into the external circuit like this. Okay, and also this current, you can see here, it has to supply this. Okay, so the reason why diode is conducting, even if I apply a reverse biases, is because the capacitor is discharging. That's a simple answer. So which capacitor is discharging? Now we know that this capacitor is much larger than this capacitor, so I'm going to assume that. Okay, so I'm not going to think about CJ anymore. I'll talk about CJ a little later on, where maybe diffusion capacitance is much smaller and only the CJ is there. So one can have a transient condition where I have only CJ there and diffusion capacitance is much smaller. Right now we are considering a situation where diffusion capacitance is much higher than the CJ. Okay, so now this capacitor is discharging and providing current in the external circuit, and this also. Of course, there has to be a continuity here, so this I know also. And this is not there. Okay, so now the issue is, for how long will the current flow? Till all the capacitors discharge, obviously, but we want to know what that amount of time is, and what is the shape of the reverse current here. How does it go? Well, let's see that. Now, it's not going to be exponential. What will be the shape? So what I'm asking is, what will be the shape of IR? The external current which is flowing through your load resistor. So we have switched it off. Will IR be constant up to a certain time and then fall to zero, or will it go exponentially? What is the nature of this IR here? This is what we would like to answer. Now to do that, look at, so you all agree that this is what is supplying current. Now if you look at C diffusion depends on what? Everything is a constant I naught. And what is I naught? Exponential function of voltage. And what is this voltage V? Voltage across these two terminals, right? This is V. So now keep in mind, it's a very important point, that C diffusion changes exponentially with voltage. C diffusion is an exponential function of voltage. Now, if you remember this, then look at this particular statement. Change in diode voltage, let's say initial diode voltage was 0.7. Initial diode voltage was 0.7. Change in diode voltage from 0.7 to 0.58 causes charge to drop to 1% of its initial value. Diffusion capacitance is exponentially related to voltage. The amount of charge that is there in this capacitance is also exponentially related to voltage. Correct? Now, let's say my initial voltage across the diode was 0.7. If I go from 0.7 to 0.58, it's easy to show when it's exponential that my charge will drop from 100% to 1%. Everybody can show that because Q diffusion is exponent QV by KT. So you calculate how much is the charge at 0.7 volt, take it as 100%. How much will be the charge at 1%, calculate how much is the voltage, you'll find is 0.58. So when the voltage across these two terminals here goes from 0.7 to 0.58, my charge drops from 100% to 1%, which means what? It's almost like my diffusion capacitance is totally discharged. So now, as it's discharging, what is the voltage across this particular terminal? What's a good assumption? It's changing from 0.7 to 0.58. And this is how much? I've applied minus 5 volt. Okay, I've applied a reverse bias of minus 5 volt. What can you assume here between these two terminals here? What's a good assumption? It's changing from 0.7 to 0.58. It's almost like constant. You have minus 5 here. If you look at the Kirchhoff's law, minus 5 and the drop here plus the drop here should be equal to 0, right? And this drop is only changing from 0.7 to 0.58. So it's a very good assumption that you can assume that during the entire discharge process, the voltage across the diode is practically constant. The voltage across this particular one is practically constant. And how much is it equal to? Well, you can take somewhere as an average. If this is 0.7, this is 0.6, maybe you can take 0.65, somewhere it's like an average here. So if the voltage across this remains constant, and this is a constant, what will happen to the current? Current will also constant. So what kind of a behavior are you going to get for IR? Can you see that I will get like this here? The moment I reverse bias it, the current minus IR will flow, keep on flowing almost a constant current till it reaches about 1% and then abruptly drop to zero. That's what I will get. Abruptly means very sharply. Obviously, nothing is abrupt. Very sharply, it will drop to zero. That's the kind of behavior that I will get if I have a model like this. Agreed? Almost constant. They will maybe, as is discharging, of course, from 0.7 to 0.58, the voltage across this one is changing. Little bit of slope may be there, little bit of decrease may be there, but hardly, compared to 5 volt here, hardly any noticeable change you are going to expect here, and then it will drop, right? It's not exponentially dropping. It's not exponentially dropping. It's going constant, conducting for a period here, and then dropping to. Any problem? If I assume my model like this here, everything is based on the model here. This is the model. It's not gone to, when will it go to reverse bias? See, it's still 0.58. It's not gone to reverse bias. Earlier it is 0.7. Now slowly is decreasing to 69, 68, 67, 66. Eventually, when it reaches to 0.58, then it's reached 1%. After that, it starts to go to reverse bias. 0.58, then it will drop to 0. Then it will eventually go -1, -2. By the time this is no longer there. Right? If this is no longer there, C diffusion has gone out now. What is left now? Cj is there. So now Cj and this, with a Cj and an R is there. And this will supply the charge here. And this Cj and R, we can calculate what is the time. That's why now the discharge, once the diffusion capacitance is over, the discharge is almost exponential, with the time constant decided by Cj and R. This Cj and R. Because note that the voltage eventually, when you reach steady state, what will be the voltage across the diode? If I've applied -5, the voltage will be -5. So from 0.7 to 0.58, this is what is supplying. Once this is gone, all the charge here is gone. Now it has to go now from 0.58 to -5. So this will supply the charge. This is going to supply here, and it's basically an RC time constant. Now it's going to go like this. It's going to go abruptly into this particular one. Okay, so this is the behavior that I'm expecting here. So now on this basis, I would like to calculate this value here, tau RR, which we call the reverse recovery time. Total amount of time that it takes for a diode to recover. Is still conducting. To recover and go into a non-conducting state. That's why I call it reverse recovery time. Time taken by a diode to recover from the conducting state and go into a blocking state. So this is the tau RR. So what we want to do is calculate this tau RR. Okay, how do we do that now? So this is the picture that we have. So now this is the capacitance which is discharging, right? So I write Q diffusion, dQ by dt. Q diffusion, everybody knows, is I naught into T naught. That's the definition of diffusion charge. So dQ by dt is equal to what? IR here plus I naught here, correct? And we are neglecting this in the initial process here. So dQ by dt is I naught plus IR. And dQ is nothing but I naught into tau naught. So this then gives me, if I look at this particular one, it gives me I naught T is equal to A exponent minus T by tau minus IR. I'm now doing more precise calculation and taking into account. Okay, fine. At T equal to 0, what is I naught? Before I switch, it was equal to the forward current, whatever forward current was flowing, right? Remember, before I went to VR, there was a forward voltage here. So there was a forward current flowing here. So I use that. I naught at 0, immediately 0 is equal to IF, forward current. And I take this here, now I put T equal to 0, and I get this expression for I0T. IF plus IR exponent minus T by tau minus IR. How do I define the reverse recovery time? When my current I naught drops to 0. So I put this equal to 0, and I put this equal to tau RR, and I get a value for tau RR, which is tau ln 1 plus IF. Okay, reverse recovery time. Do I know IR? Can I calculate IR? How do I calculate IR? This is minus 5. What is the voltage from here to here? Minus 0.7 and sorry, plus 0.7 here. And so you can, and then there's a resistance. So you can calculate what is IR. How do I calculate forward current? Well, if this was VF, the voltage drop was 0.7. VF minus 0.7 divided by R gives you the forward current. So you can calculate IF, you can calculate IR, you know tau, this should be tau 0. Everywhere I should have put tau 0 here, and we can get an estimate for tau R. Okay, so this is what our model is telling, how a diode is switching off. Okay, now this is the model that you see here, CJ, I0, C diffusion. This is the model that is normally put in circuit simulators. You know, when you want to simulate a diode, in the circuit simulator, there is a model for CJ, there is I0 exponential model here, and there's a model for diffusion capacitance. Okay, so for example, I went to microcap. Microcap is a circuit simulator that many of you may be familiar. And in this microcap, what I did was I switched from 5 volt to minus 2 volt. And I put a 13.2K resistor here. And the lifetime, this tau naught I put as some 100 nanosecond. And deliberately I removed the effect of CJ. I made CJ very, very small. Okay, CJ very small. And then note that I'm switching. I'm going from plus 5 to minus 2, right? Plus 5 here. Input voltage to the diode, and I'm going to minus 2 here. What does microcap say? Well, plus 5, there's certain current flowing here. When you switch, there's a current flowing. Can you see that current flowing here? And then it quickly drops to 0. Drops to 0 here and then remains 0. Once it's gone into a blocking state, it remains 0. How much time did microcap give me? Well, about 76 nanoseconds. Is the time for which my diode is conducting in the reverse bias case. How much is this? Tau ln 1 plus IF by IR gives me 95 nanoseconds. So this is approximate because I've assumed it to be entirely, the diode drop may not be exactly 0.7. I made some simplifying assumptions here, but it's reasonably close for a very crude calculation. 95 here and 76 here. If I take in the diode drops and all that properly, and note also, can you see here there's a little bit of change in current here? It's not entirely flat, entirely constant. Can you see here? It starts from here and then goes a little bit. You can detect there is some change here, right? Why? Because the voltage across the diode doesn't remain constant, as we saw, from 0.7 to, it keeps on changing there. Okay. So this is the behavior that we expect based on the model here. And this is the model that is normally put in the circuit simulators. They have this model here. But this is not what you get in real life. That's where the trouble comes. Real life, you don't see this kind of a behavior. Now, I said the whole model is based on quasi-static assumption. What is this quasi-static assumption? And when I'm calculating diffusion capacitance here, when I write diffusion capacitance like this here, it's all based on quasi-static assumption. And what is this quasi-static assumption? If you recall, under static case, what did we say? Hole density in a P plus N junction goes like this, right? Now we are saying under transient case also, the behavior remains the same, but as the voltage across the diode drops from 0.7 to 0.69, 0.68 and all that, what happens? Well, the shape remains the same, it just comes like this here. The shape remains the same, it comes here. And the shape remains the same, it comes here. It goes like that. That the transient case is almost like a series of static cases. The transient is a series of static cases here. This is 0.7, this is 0.69, there's maybe 0.65 and then 0.5 and and 0.58 and all that. We're assuming that even under transient condition, the whole density profile and all of that, they remain the same as if it's under the static case. Except that this voltage here, remember who decides what is the value here? The voltage. Excess voltage. The voltage is time varying, and so as the voltage changes, it drops. But the shape is remaining the same, just like a static case. And so we say transient condition is being modeled as a series of static cases. It's as if my diode is all the time, in this, but the amount of charge and all that is changing with time. But this is not what is. So we say the shape and everything remains the same, as you can see here, except that Vd becomes a function of time. But remember, how did we calculate this here? Exponent minus x by LP, where did it come from? that this shape, where did it come from? Continuity equation, right? The shape came from continuity equation. Continuity equation has what? It starts from what? Del P by del T equal to so much. And what did we, when we got this shape, what did we assume? Del P by del T is 0. Now del P by del T is not 0. It's not 0. So I won't have this shape. This shape is only in the steady state. But I'm assuming the shape remains the same. Shape of the whole density profile remains the same, except that only this becomes a function of time. And it just keeps on reducing like this. Okay, so this is what is known as quasi-static assumption here. Right? So we derive an expression for capacitance. Remember, how did we derive an expression for capacitance? We say C equal to del Q by del V. How did we get Q? Q, we said we'll integrate P as a function of voltage here. Right? And where do we get P? P we get from static case. P we are getting from static case. But the meaning of capacitance is transient. So how can I do that? You're seeing there's a problem here. To get capacitance, C del Q by del V. Del Q by del V here. I need Q. And Q is Q P dx. How do I get P? I'm using P from static variation. And then using it. And substituting and calculating expression for capacitance. And capacitance is used all under transient condition. It has no meaning in static. Okay? So that's the problem. Now you may say, why don't you get P from, not from static case, but you get P from by actually solving the continuity equation. Now continuity equation becomes what? It's a partial differential equation it becomes. There is a P which is varying with T and P which is varying with X. It becomes difficult. It becomes difficult to handle. In fact, the solutions are fairly complex. But now look at the consequence of my quasi-static assumption. So diode is a beautiful device which shows that if you make quasi-static assumption or you don't make quasi-static assumption, what are the implications? Okay. So remember, when we are making quasi-static assumption and we use the model that we just saw, we expect like this here, right? Actual diodes show you what? They show like this. They show you like this. Look at the difference. There is a region of constant charge here, but there's a fairly large region here which is varying with time, where the current is varying with time. This picture that you see here is what is the actual picture of the diode reverse recovery here. It's not that it's almost constant, and this one would be a very, very small region here. Now this one, in fact, is the dominant region. Okay, let me show you. This is from our 380 lab, 1N4007. The TAs and other students may remember doing this experiment, 1N4007. When you do, look at this diode reverse recovery. So we have, this is the forward voltage here, and we immediately switch it to reverse voltage, and look at how the diode is switching off. There's a constant part, and then there is a well-defined this part here. This one here. I'll show you some simulation results here. So now what is happening is that there is a well-defined this region here, fairly large region here, this one, which is not predicted by our normal quasi-static model. Now, if you go ahead and I'll show you a simulation result, look at how hole density is actually varying. This is the hole density at time t equal to 0 when the diode was in forward bias, right? P plus N junction, standard exponentially decreasing. When I reverse bias it, what did we expect? How should it go? It should fall just like exponential, it should fall. This is at a certain time, a few, maybe tens of nanoseconds after I've switched off. Look at the nature of the graph. It's not the same as static case. Can you see here? Look at the shape here. Very distinct. The shape, look at the shape here. It's not, which we know that my P under transient case should not follow this behavior here. This is only under static case. Under transient case is following like this here. Now this is interesting. If you look at a P which is going like this here, what is it indicating? Look at this P here, hole density, which is going like this. What is it telling you? If you see here, all right, let's see here, the hole density is decreasing. In which direction are the holes diffusing? They're diffusing right, okay? But if you come here, which direction are the holes diffusing? Left. Where are they going? What is on the left? Depletion, and then P plus region here. Where are they going? Back to the P plus region here. They're going back to the P plus. Now they're going back to the P plus here. So holes are going back into the P plus, and then where will they go? Okay, so and here is where, and once they diffuse here, where will they go? What happens to the holes? They'll all recombine. So here, when they're, so what is happening is the holes are going here towards the right, and they're all recombining. And when they're going left, what is happening? They're going into the P plus and flowing out through the external circuit. So what is happening is, you can see here. So there is a, if you look at this hole density here, and look at the current. So current is simply derivative of, because hole current is predominantly diffuser, right? So it's derivative. So look at the green line. Can you see negative current here? Negative current, and then a positive current, which is here. Look at the hole current, and then eventually hole current becomes zero. The green curve that you see here. Okay, which you can get from this graph that you see. Okay, so what is happening is this now. Look at this picture now. I've shown you how actual hole density falls. Look at the way hole density is falling. Now remember, our quasi-static picture was what? Hole density is going like this. It's the same shape and is dropping exponentially like this, like this, like this. This is the quasi-static picture. And the actual picture now, see here. See how it drops. Starts from, this is a steady state. Then it goes like this, goes like this, goes like this, here, drops here, and drops. And then after I've not shown, then it will continuously drop and eventually go to zero here. That's how it is dropping. The shape, if you look at it, is very different. Fairly differently. Now, can you also see now, we said that this, as it is discharging, it supplies what? The current in the external circuit, and it supplies this also. Can you see from this picture? Both these components here, this one and this one. Can you see both the components or not? Where is this component here? This is diffusing, right? It's diffusing here towards the left here. This is this component here. And where is this component? All this recombination that is happening here, right? This part here. So you can clearly see that this is there. Now in the previous picture, if I assume that it goes like this only, then where does this current come from then? There's nothing going back, right? If I assume that my hole density profile just goes like this here, exponentially like this, then there's nothing going back, right? There's nothing going back here. So that picture is inconsistent. That picture is not right. It's a simple picture, but it's actually not right. This is what is actually happening. This is how my diode is discharging. So very different from simply going like this. And there are two distinct phases here. Okay, so I'll not go into the details now. So what you are seeing here is my hole density profile. It goes from here, 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 and eventually it comes here. Now, when the hole density is going from here to here to here to here, what do you think is the change in the diode voltage? How much? See, diode voltage here is 0.7. What do you think will be the diode voltage here? Almost 0.7, because diode voltage, this hole density is related to diode voltage by exponential relationship. Remember, delta P is exponent QV by KT. So as it goes from here to here to here to here, in fact, the diode voltage is not much changing. It's not much changing. That's why the voltage is constant. The moment it drops to almost zero here, now the voltage here, this thing here, now this part is controlled by this part here, a diffusive process. So this end, when it drops to zero here, is this particular point. And after that, all this part that you see here, this part is coming from all this charge that you see here, all this charge. Now it slowly recombines and some of it keeps on flowing there. But diode voltage has no effect now. It's not controlled by diode voltage anymore. It's controlled by how this particular capacitance is, how this particular charge is diffusing towards the right. And that decides diffusion and recombination decides this particular part. Earlier, the amount of voltage here was decided by the external current, the external resistor and all that, because diode voltage was almost constant here, and Kirchhoff's law will give me the current that flows here. But the moment you reach this particular point, that's not the controlling state here. This diffusion and recombination controls and you get this particular part. Okay. Some more simulation results. So this is from Silvaco P plus and diode here. So you can see how the current actually goes here. Right. So this is I've deliberately taken a slower diode with 1 microsecond tau p to see the effects of diffusion capacitance more here. So you can clearly see that this part, the constant part that you see here. So this is where it has gone to 90% of its value here. So it's about 0.6 microsecond. And the whole thing, by the time it decays, where it goes to 10% of its value, is 1.4 microsecond here. So this is about, constant part is about 0.6, and this decaying part that you see here is about 0.8 microsecond. And this whole thing is because of diffusion capacitance discharging. So as the diffusion capacitance discharges, one part is a constant part, and the other part is this more complicated part. Not entirely exponential, but more complicated part. So it's, and the overall thing is, and if I use my simple formula here, it predicts 0.95 microseconds as my total reverse recovery time. Now, reverse recovery time now you see is more complicated. So it's actually, if I look at it till it's fallen to 10%, it's actually 1.4 microseconds. So this does not give you the right answer. It sort of predicts same order, 1 microsecond, 1.4 microsecond, but accurate value you don't get it from. You have to do more detailed analysis to see what happens. Okay, and so constant. So this is a signature constant, and this whole thing is due to diffusion capacitance. There's no junction capacitance coming in there. So next, what I did was, so here what we did was switching from 5 volt, where there's 5 volt, there's a lot of forward bias current, and there's a lot of diffusion capacitance, and then we went to -2. In the next case, what I did was, what I did was I switched from 5 volt, from 0.5 volt. So I applied 0.5 here, and then I went to -2. So when I apply 0.5 here, in the forward bias, what would happen? Not enough voltage to forward bias the diode, so there's no diffusion capacitance. So this is not there. Right? I only get the junction capacitance. And then from 0.5, I went to -2. Right? Same diode in simulation. And look at the transient. So this transient is coming when there's no diffusion capacitance, there's no constant portion, and there's only the junction capacitance charging. And it charges in what? Roughly about less than 0.2 microsecond. Less than 0.2 microsecond. So the junction capacitance is roughly charging in maybe 0.1 to 0.2 microsecond. That's the time scale here. And compare that to your this charging. Right? So this entire that you see here about 1.4, all this is the diffusion capacitance. Once the diffusion capacitance discharges, then the junction capacitance will take another 0.1 or 0.2 microsecond to completely charge up to -2 volt. So is dominated by the diffusion capacitance. The discharge is dominated by diffusion capacitance and is far more complicated. Okay. And one clearly sees the effect of non-quasi-static behavior here. Quasi-static would have predicted a constant current up to 0.95 microsecond and abruptly dropping to 0. Here, it predicts a constant, but then it predicts this part here also, which is fairly significant part here. Okay, and all this is because of the carrier density profile is very different under transient case as compared to the static case. As I said, the way to do this would have been to take a continuity equation, time-dependent continuity equation, and get a expression for P and then take its derivative and calculate that. So that's complicated. For those of you who are interested, you can go to this book, one of the books that we have recommended by Simon Z, SMZ, Physics of Semiconductors. In the chapter on PN junction, you will have a little bit more discussion. So there also, only the formulas are given for how this carrier density changes here, but a reference is provided on how to calculate this density profile here. So for those of you who are interested, may go to a particular reference and read how to solve the time dependent continuity equation and then get the carrier density profile and get the entire transit. Okay, so let's stop here.